right? Um, we'll be looking at regression. The lesson is about linear regression. Now, we are going to have to define what we mean by regression. But then, let's look at the famous linear equation, which you must have learned in high school, y equals to mx plus c, y being the dependent variable, m being the slope. And then x being the independent variable and c being the constant, the intercept actually, it's an intercept. Now, the concept of a simple linear regression is an extension of this equation that you are seeing here. So it's just, okay, the normal stuff, but a number of other things added, but it's an equation nonetheless, and it looks something like this. Now, regression can be defined as a statistical measure of the average relationship between between dependent variables, and it may be one dependent variable, it may be many dependent variables, and then you have at least one independent variable. So you may have one independent variable and you may have many independent variables. And now the relationship can be positive or negative. It may be linear or not linear. Now, when you have a data set and you plot it, maybe you collected data and somewhat you plot the data for two variables now, x and y. You should know already that you have, you have y here, and this is x. You have y here, this is x. All right. Now, assuming you plot the graph of y and x here, and then you are having something that looks like a straight line, then it means the relationship between them is linear. That's why it's looking like a straight line. It may not be perfectly straight. Some points may lie out. You may have some points here and there, but predominantly it's going in a linear form, a straight line. Then it means that there is a linear relationship between them. On the other hand, if you have a curve, something like this, and it's not always like this, it may be like this sometimes. It may even be any kind of curve. That means it's not a linear relationship. Sometimes you may have a combination of the two. It's linear up to some point, and then maybe it begins to form a curve at some other point. That means the relationship is curvilinear. All right. Now we can go on. So you have an idea of what regression is now. A relationship between two variables in such a way that they are related. It may be linear, it may not be linear. So let's go on. Let's look at linear regression. Now, linear regression can be defined as a measure of the average relationship between a dependent variable and at least one independent variable. Now, you have just one variable, but the relationship is expressed using the equation of a straight line, as I said earlier, and that's what makes it linear, actually. So you may have more than one variable, and you may have just one variable. If you have just one variable, you call it linear, simple linear regression, which is the case here. All right, so the simple linear regression. But in a situation where you have more than one dependent variables, so say x1, x2, xn, whereas you have just x here, you have x1, x2, and continues like that until you don't know what n may be. So n may be 9, n may be 20, n may be 100. Okay, are the independent variables. So x1 to xn are the independent variables. And we have the coefficient of the x1, x2, and xn. All right, now going back to this simple linear regression, you have just one independent variable. And don't forget, there is a term here that we have added that is called the error term. That one is not found in your you don't find that in your linear equation, y equals to mx plus c. And so that's the difference here. If you look at this very well closely, you find out that just turning it a bit, what we have written here is just putting this here, bx plus alpha. All right, so whatever you have here, these two are the same. Actually, these two are the same, but there is an added stuff. That's why I call it an extension of the linear equation. So you don't add this one to your linear equation, the error term here. Let's just call it E for now. All right, you don't add the E here, so that's that. And as we go on, it's important for you to remember that your simple linear regression looks something like this. So you have just an average relationship so it follows the equation of a straight line. You remember that, and you have at least one independent. Okay, you have in the simple linear regression you have just one independent variable, but in the multiple linear regression you have more than one the independent variables. So you have more than one independent variable here. You have just one independent variable here. So there is something that is missing in our definition of a linear regression that we need to put. A linear regression can be defined as a measure of the average linear. The word linear has to show there to show that it is it follows a straight line equation, or like it gives a straight line when you plot it, at least approximately. All right, now so yes, we're estimating the relationship actually. The actual relationship will not be a perfect straight line, and that's why we account for the error term. But the estimated relationship which we are going to obtain will definitely be along a straight line. So going back to what we did the other time, typically when you have a data set and you have plotted it and it looks something like this, I said some points may be here and there, our regression line tends to go across it somewhat in a straight line. So that's that about that. Now we move on. What do we now do with all of this? We need to find a way, because our concern is actually the simple linear regression. So let's look at it again. As we said before, the intercept alpha is the intercept. It's a constant. It's the intercept of your regression equation, and you have y to be the dependent variable. You have x to be the independent variable. You have b to be the slope or coefficient of x. Now, simple linear regression can be defined as the average, all right? The average linear relationship between a dependent variable and an independent variable. Now, so now you have that definition. Now, so we again, we said simple linear regression can be defined as a measure of the average linear relationship between a dependent variable and one independent variable. Now, let's look at possible shapes, the possible shapes we can have when we have a linear or a simple linear regression rather, when we have a simple linear regression. Now, the shapes the shape can change with respect to the slope. All right, now so when the slope is positive, your equation tends to go somewhere like this. You tend to have something like this going upward in a straight line. But when it is negative, your regression definitely will come down. But please be aware that it may not necessarily start from the origin. So your equation will start from here. It may start from here. It depends, but it will just be a straight line. All right. But when the slope is negative, it will come downward. All right. Now, when the slope is 0, that means that y is constant. For every x value of x you take, every value of the independent variable you take, you are going to have the same value. So just one y, but you may have different x's. Now that's what we are saying in this case when the slope is 0. So just picture that. You can see that from here. When this is 0, let's forget about the error term for now. Let's assume that the error term is also not there. But when the slope is 0, anything you put as the value of x will become 0. So you always have y to be alpha. That's what we are talking about. Now, we move on. It is important to obtain the slope and intercept for this equation. So you have alpha and beta there, but you need to know how to obtain them. And it can be shown that alpha is equal to y bar minus beta multiplied by x bar, and beta equals to the n multiplied summation of the summation of x times y, and minus the summation of x, all in bracket now, multiplying the summation of y. So n multiplied by summation of x squared minus summation of x all raised to the power 2. So you have this as the denominator. Now that is how you can obtain them. But let's look at how we derived this. We didn't just get these two from, we didn't just get them from nowhere. We got them by doing some things. Now look at something here. Now look at the equation we have on the board. This time around we are putting I here to show that it can change values. Please bear with me. There's supposed to be an x here, xi. So xi. All right, now so if we let y be equal to what you have here, then definitely you are going to, y cap, just call this y or y hat. So if you let that y hat be equal to alpha plus beta, then this equation here becomes this. All right, so the first equation becomes the second equation. First, second. Now, which means that yi is the observed value. So we are saying that originally when you did your observation, maybe you recorded the data set, you had yi to be the original value, right? Because we are accounting for this error term in that if we estimate this particular value, we may not have exactly what is in the observation. So the error here is adding up to give us back what was originally in the observation. Now, by looking for the difference between the observed observation, this one, and the estimated observation, this one, then estimated, please, then we can actually square this difference and sum up for every single observation. If we do that, then we are going to have what you're seeing on the board, and then we can substitute. Sorry, I want you to know that this should not be part of it. Okay, so this should not be part of it. E cannot show there again. So this is what you should have. This is what you should have. Now, if this is the case, so E is equal to that, and you put that there, then you get y minus alpha plus, and don't forget xi is supposed to be here. You're supposed to have an xi here, so b alpha plus b multiplied by x raised to the power of I, plus beta times x subscript I, this is a subscript, please. Let me take that again. Okay, so y is this. Now we go on. Y minus alpha plus beta xi. All right, when we do that, we have substituted this all of this in place of y at, and then we go on yi minus, so we now open the bracket and we have this. Then we minimize with respect to alpha the first time. Now, if you have done calculus, and I believe you have, you find out that minimization technique is one of the use of your differential calculus, or one of the application of differential calculus. And what you are trying to do is to find the value for which this particular expression we have here, this one, which is equal to this, the value for which it is smallest. Okay, sorry, there's supposed to be a summation here. All right, so summation here, that summation from I equals to 1 to n. So it's that summation that will become this one. So that summation becomes this. Now, we are trying to look for the value of alpha and beta for which this will have the smallest value, so that when we sum all the errors and when we square all the errors and sum them, we have a very small value. So the values of alpha and beta for which this error here is small, has the smallest value. This quantity here rather has the smallest value, is what we are trying to find and look for. And when we have that, we believe that this particular alpha and the particular beta will be the particular alpha and the particular beta obtained will be the best estimators that we want. So estimator is just like something like an equation that results in a value when you evaluate it. So an equation, so alpha, for instance, if you have an estimator for alpha, it will be equal to, it's a function of something, and that of beta also is a function of something, actually, x and y, function of x and y. And then when we have obtained them, we can use them in obtaining our regression model. Now, looking at this, we go on, evaluate that, and when we evaluate that, okay, I think I'll go slowly so that you can see what we are doing. When you evaluate that, at the end of the day, don't forget that whenever you have yi or xi, you have a variable. But alpha and beta are constant, so they can always come out of the summation sign. So now, if you continue using that approach, you find out that beta eventually, alpha left earlier, okay, because alpha is a constant, summing it over, summing it from like n times, that's what this means, it will become n alpha. So, but beta, though a constant, xi is not a constant, and so beta goes out of the equation. Xi is summed from, okay, 1 to n, and when you do the equation, well, you have an equal to sign here, you end up getting something like this. And so summation of xi, you should remember this, that this will give you x bar, there is a bar there, please, x bar, and this will also give you y bar. That's the mean for y, the mean for x, mean for x, mean for y. And so when you rearrange the equation, you get this equation. So that gives us our expression for alpha. Now, ordinarily, you should write a cap for all the alphas that you write after the minimization here, after you have done this. From here, you should begin to have cap on alpha and beta, but I'm not doing that because of what I'm using. So you should know that. So this means that it's an estimate. Just like we did for y, if you remember, we did that for y. So y cap, so meaning that it's an estimate. And we had said that here. All right, so we go on, and then we've obtained that of alpha. Now doing your mathematics again, you minimize with respect to beta. That means you do a partial derivative with respect to beta, and then you equate it to 0. And that way you continue doing all the mathematics there. As you continue, this is equal to, as you continue, at the end of the day, you get beta to be equal to what we have on the board. Now, that's going to be it. So what we have on the board may look a gigantic kind of formula, but it's not anything that is difficult. It's not a difficult stuff. Now, let's go on and see what we have. What we have is this. All right. Sorry about the Zoom stuff, the software error actually. They obtained estimators for the parameters. So the parameter alpha has its own to be this way. So, and then that of beta is this way. Now we're going to look at how to use that. Now that we already know what our estimators are, so let's look at an example. We want to look at this example. The example says obtain a regression model using the data on patients admitted in PYZ hospital below. Now look at this. The question now is, how do we know which one is our independent variable and which one is our dependent variable? Now, we were only told to obtain a regression model. We were not told which one is. So in reality, you will not be told that this is the dependent variable. If you are the one collecting the data yourself, you are the one who have to determine and say, okay, this is it. If you're collecting the primary data, fresh data by yourself, you have to be the one to think and say, okay, this is dependent, this is independent. You sit down. But if somebody else has done it, they may tell you that, okay, this is the dependent variable, this is the independent variable. So you need to know how to relate variables with one another. Now, looking at this, to solve this problem accurately, we need to answer the following three questions. Which of the variables will be our independent variable? That's the first question. The second question is, which of these variables, here, because we have patient, we have weight, we have calorie intake. Now, which of them will be the dependent variable? The third question is, which of the variables should not be used for obtaining the regression model? Because we want to actually obtain a linear regression model, a simple linear regression model. So obtain a simple linear regression model using the data on patients admitted in PYZ hospital below. So look at this now. We are looking at this, and you might be guessing already that, okay, this or that should be it. So take your time. All right, while you're at that, you need to be very careful. If you take your independent variable to be the dependent variable, you mix them, your result will not be correct. So you must be careful not to mix the variables, not to take y for x and x for y. So let's look at the solution. All right, now so the independent variable is the calorie intake, the weight is the dependent variable, and the variable labeled patient should not be used. That's just like a serial number, just to identify that one patient is different. Okay, that this data, for instance, belongs to one patient. The first one, the second one belongs to another patient, and like that onto the fifth one. All right, now, so the weight is dependent on the calorie intake. You're definitely a person who has or who takes in more calories should have more weight. So, but your weight does not determine the calorie intake, because you may have, weight gain actually depends on calorie intake, but calorie intake is not dependent on the weight. Somebody may have, perhaps of natural cause anyway, he may have more weight than another person and may not take as much calorie as that person. But we are saying on when you take more calorie, taking more calorie should actually gain more weight. All right, now so there are cases like that you, for instance, you already know that somebody who eats much should have more weight, but you may also be able to say that a person who, well, it depends, but you should be able to tell that, okay, now if this is done, it should affect this, and then, all right, for instance, age, to a certain extent, age actually affects your weight. Okay, it also affects your height to a certain extent. For instance, a person who is 2 years old cannot be as tall as somebody who is 20 years old. Okay. Now, so that's that for height. So that means your age actually affects your height. Like that, there are so many of them, but we can continue. Now, the weight is dependent on calorie intake, because the more calorie you take, all things being equal, and that's true, over time, the greater your weight will be. Now, going on, we have our equation is so that which we'll be using to predict. Mind you, don't forget, actually we call this something like this, and this one here, but at this point we just neglect that, but you may do well to put this here in case you are using it to predict and you want to put a distinction between the observed value, which is, this is the observed value now, yi, all right, and the predicted value. This is the equation you're going to use to predict. All right, now, so we now need to obtain, okay, summation xy. Now, since weights are y, the dependent value, just need to add everything here straight down, 60 plus 45 plus 73 plus 61 plus 82. That will give us 321. Now you add everything here straight down, 2 plus 1.3 plus 3 plus 1.7 plus 2.1, that gives you 10.1. Now you, to obtain this one, this means x times y. So 60 times 2, 120, 45 times 1.3, 58.5, 73 times 3, 219, 61 times 1.7, that's going to be 103.7, 82 times 2.1, that's going to be 172.2. All right. Now we need to sum everything straight down as we did before for the others. We get 673.4. Then we go on to this one. We square our x. So you square 2, you get 4. You square 1.3, you get 1.69. You square 3, you get 9. You square 1.7, you get 2.89. You square 2.1, and you get 4.41. And then you sum everything straight down like that. You get 21.99. All right. Now you look for the average for y. You should be familiar with this this equation here. Y bar equals to the summation of yi over n. So n takes values from 1 to 5, because I takes values from 1 to n, and n is 5 here. So we put 5 in place of n there, and then we have 64.2. Then we look for x bar. X bar, we get it to be 10.1 divided by 5. That will be 2.02. You already know we have summation xi and summation xy from this place. All right. Now we go on to look for our beta. Substituting all the values that we obtained here into this equation and substituting correctly, we will end up getting 15.7305. All right. Now, going on, we obtained y bar and x bar earlier on, and so we just put their values here. Now y bar was obtained to be 64.2, so putting y bar here, we get this. And then x bar was obtained to be 2.02, so putting x bar there, and then we put beta, 15.7305 here, and then multiply and subtract from this, and that will give you 32.4244. Now, when we go on, our equation, we only have obtained the parameters which are beta and, right, so if you don't mind, if you like, you can, at this point, you may put the cap there, but it's actually supposed to be there to show that it's an estimate. So let's just put it. Right? So you may also do well to write this here. Well, in this case, this is actually a depiction of the true thing. So if it is left this way, it's not a bad thing anyway. But right. So if okay, so now we obtain theta. Beta rather, and alpha. But how do we go about it? Now remember that the equation we wrote earlier on, which I said we could leave the hat out of it because this is a depiction of the true thing, trying to talk about the way it should be. This is not the estimated value, but this one is the estimated value, so you should have a hat here. Now, looking at this, we know that alpha in our equation is this, and we obtained it to be what you are seeing now. We obtained it to be 32.4244. So we just put it there. So alpha, you can see it here, you put it here. Now looking at beta, beta should be with xi. Beta should be with xi, and we just put our beta there, and we obtained it to be 15.7305 up there. So we put it in place of beta and multiply by xi. So that's how we get our equation. So this is what we are looking for. This is our equation. So we've obtained the equation, but what do we now do with the equation that we have obtained? We can predict. So we may, in a normal, like you're given a regression equation or something, regression, okay, a particular data set, and then you are asked to feed the data, feed a line to the data or something. So the line of best fit, how do you do that? Your regression line is going to give us the line of best fit. So somehow the equation may be in a straight, maybe approximately straight line anyway, but you don't know which line should be the line of best fit. So your data will help you when you fit a regression model to it. And that way you can now know, okay, the line of best fit. Now that's what we do. But then we use this to predict. We know that there can be some errors. I talked about that earlier on. I talked about the error term. You will have a discrepancy between the original value, which I called yi, that's the observed value, and the estimated value, which I call this. All right. Now, which is what we are obtaining with our equation. Now, if we do this, then there should be an I here, please. If you do this, all right, then we are going to have, okay, if we obtain this, then we'll have a discrepancy from this. That's what led to the error thing we're talking about. So E equals to yi minus y hat. So if you put your hat here, it's not wrong to do so, but we put it here already to show that, and we've put this to show that these two are estimates. Now coming back here, we know that there will be an error actually, but at least we could predict, and that was why we obtained least square estimates at the other time when we did some minimization stuff. That's why we obtained least square estimates. I'll go back there shortly of this. All right. Okay. Let's look at it. Let's take a look at what I'm talking about. Now, there are a number of methods for obtaining your parameter. The other time I was talking about estimating the parameters of the simple linear regression. One of the method is the least square estimate. Least square methods of obtaining the estimate. So the least square method is what we did here actually, and what we're trying to talk about is that we are talking about the fact that you obtain a difference between y and y, the observed value, and the estimated value, which I have written here. You can see that yi and then y hat. Now, but when this is minimized, so it means you have the least squares. So it means that you have a parameter that will help you obtain estimated values that are not far, from the observed value, so that when you find the difference between these, it's very close to zero. It may not be zero, it may even be bigger, but it will be close to zero, like it will be small. The gap between these two will be small. So, for instance, 1 is closer to 0 than 2, all right, and 4 is closer to 0 than 9. So we are saying that the error will be minimized. So it may be bigger, but it will be minimized. So the minimum possible, or rather, it will be minimized. Yes, we may say the minimum possible error will be obtained when you use the least square method. All right. So looking at that, we go back to our prediction. So we now want to predict. So assuming that we have a patient who takes in 4 megacalories, what will be the weight of that patient? Now we're trying to see what the patient's weight will be. A normal human being, I think from what I saw online, actually, should take between 2,000 to 2,500. Okay, well, it's data anyway, but I think a human being needs that around that range from what I read. Anyway, but this man is taking 4. That's about times 2 of what some other persons may take. Now, so what's going to be the weight of that patient? 95.3464. Now, how do we obtain that? We already know that we have been given a value for our x, which is 4 megacalories. And then when we take our equation, wherever we find our xi, we put the 4, which is what we've been given there. And so multiply 4 by 15.7305 and add it to 32.4244, and then we get 95.3464 kg. So that's that. So the regression equation is very useful, very, very useful, because it could actually help you obtain relationship between 2 variables. We talked about that. And don't forget, you need to be careful when you are not told which variable is dependent on the other. So you need to think about it very well. Which one should affect the other? The variable that affects another is independent. The variable that is affected is dependent. The variable that is affected by another variable, that it doesn't have a value of its own, but when you change the value of a particular variable, it changes. So it assumes variable based, or it assumes values based on what, based on the values that another variable assumes. So if x is 2 and y changes to 4, then you may say y is equal to maybe 2x, so that equals to 2 times, so when x is 2, then y is 4. So if x changes to 3, for instance, y will become 6. All right, so you see that now that y is dependent on x. So you need to think about that at any point in time, that which one of them affects the other. All right, so that will be the end of this lesson.